Good morning. We are very happy to have today the second part of the mini course of Juan Rivera-Letelier. So please.
Okay, thank you. All right, so I wanted to make a brief review of what we saw yesterday about the Artin-Mazur zeta function. So we are considering a topological space, continuous map from X cubic cells. And we want to count the number of periodic points. Now, for the Artin-Mazur zeta function, we count periodic points of a given period, even if that period is not the minimal period of the periodic point. So, define n sub n of f as the set of fixed points of f. Now, this gives us a sequence as we vary n, and we then build the Artin-Mazur zeta function is defined by this exponential so it's not quite the generating function, but close. So the logarithmic derivative of this function is the generating function up to a factor of s, but it's somehow convenient to, we will see later that it's convenient to write it in this way with exponential 1 over n. All right. Okay, so, and we discussed the case of rational maps, complex rational maps. So if we have a rational map of degree d, then we saw that the expected formula for the Artin-Mazur zeta function is relatively simple. There's 1 over 1 minus d times s, and this is provided that there are no parabolic cycles. Now, in general, so if there are parabolic cycles, then we just get some extra factors. But in all of the cases, the Artin-Mazur zeta function is a rational function of s.
Does this include operative periodicity?
Yeah. Yes.
Do you count them multiplicity?
No multiplicity. So the multiplicity issue comes with the parabolic.
This
Yeah. Yeah. So super attracting cycles are
because they are
have multiplicity 1. Yeah. So as periodic points, they have multiplicity 1. Yeah. So the issue is parabolic cycles, and they yeah, exactly. And then they just translate into an extra factor. So basically, you're missing certain orbits. Okay. All right. I mentioned a couple of problems. So I don't really know what happens if we have complex correspondence, acting on a Riemann surface, compact Riemann surface. That would be an interesting problem. I also mentioned the case of positive characteristic, where perhaps the expectation is that the theta function is always transcendental. And then Paulina mentioned this example that maybe I should have thought about. So another natural problem would be to consider rational functions defined over QP. That would be also an interesting case, I think. So maybe just write it down. Then we consider a rational function with p-adic coefficients, and we maybe want to consider this as a map from well, maybe we want to add infinity. So this would be a map from the projective line of QP over to itself. And the question would be whether so is the Artin-Mazur zeta function rational. For quadratic polynomials, they have a very simple structure p-adically. So either you have a some type of Julia set where the dynamics is conjugate to a full shift into symbols, and then we have rationality, or we have this good reduction case, and for QP that means that there are a finite number of periodic orbits, and in that case it's also rational. So well, of course, I mean, it could be significantly more complicated in higher degrees, but maybe the expectation, I mean, if I had to bet, I would put my money on the Artin-Mazur zeta function being rational. Now, this is also interesting because you have the action on, there's this tree, this regular tree, the Ruelle building of P1 of QP. It's a regular tree where the degree is P plus 1 in every vertex, and this rational map acts on this tree. And it's not that different from, say, I mean, it's relatively close to the interval case where this tree is mostly mapped to itself as a simplicial map, which is almost one-to-one, except at finitely many folding points. So, I mean, maybe it looks like an interesting case to study. All right. Okay, so let's maybe move on to interval maps. So here we have an interval and a continuous map. This is a multimodal map. Now, this means that it is continuous. non-injective, so we don't want to. We want to avoid trivial cases and piecewise monotone. So we can partition I into intervals where f is finitely many intervals where f is monotone on each of the intervals. Now, I mean, in most cases, perhaps I want to restrict to some put some additional conditions that are not completely necessary for everything I'm going to say, but just to be on the safe side, I will suppose that f is either piecewise expanding so this means that again, there's a partition where it doesn't need to be differentiable, but we do want we do want to have a partition where the map expands the distance by a factor, at least. Okay. Or perhaps we want to include critical points. Say we want to include also the quadratic family or polynomials. So we also want to include some regular cases. So maybe C3 with negative Thurston derivative. Okay, so two hypotheses mainly to avoid some some non-essential issues. It's more like to avoid some pathologies, if you like. All right, so two, yeah.
C3 extending slightly.
I would say maybe C3 up to the on all of I. So it has yeah. So
you don't. Oh, I mean that is.
Oh, in this here, yeah. No, oh yeah. It could have a Lorentz like. Yeah, it could have infinite. We want this to be continuous though, and it could be it could have derivative going to infinity. Yeah. So what I'm going to say is mostly topological, but we do want to say avoid having, say, an interval of fixed points. That's what basically I want to avoid. All right, so before we can define the lab number to be the number of monotonicity intervals. And then we have the growth number is the limit of the lab numbers of the iterates normalized. And I forgot to make a very important observation here. Yesterday, which is that this growth number is equal to the exponential of the topological pressure. This is the content of the theorem by Rivera-Letelier. And like
Pressure.
oh, topological entropy. And, yeah, sure. Yeah, pressure we have later. Yeah. Okay. So, oh, I forgot the thing here.
Yes.
Okay, thanks. Right. Okay, some consequences. Of the work. Milnor and Thurston. Okay, so the first one is that the Artin-Mazur zeta function extends to a metamorphic function defined on the unit disk. Okay, so another consequence is that there is a very sharp dichotomy, actually. So it's either rational or as the unit disk as a natural domain. So this is saying that either it's defined everywhere in the complex plane, or you cannot extend it to any single point of the boundary, right? So there's no way to extend that. If you could extend it just a little bit on some neighborhood on the boundary, then in fact, it was a rational map and you can define it everywhere. Okay. So it's a very sharp dichotomy. And in particular, so in the latter case, so this implies that this is transcendental over field of rational maps. And maybe let me have here. So in the case where we have positive entropy, then 1 over the growth number is a simple pole of the zeta function. And it's also the smallest pole, so the pole with the smallest norm. All right, so as I mentioned yesterday, you can use this information with combine it with a Cauchy estimate to show that in fact the number of periodic points grows pretty closely like gamma f to the n. Okay, so this somehow, so what to say is that using these properties you can extract information about the growth of periodic points. So we cannot maybe have a formula in the case where the zeta function is transcendental, but we can say up to some certain order how the periodic points grow, the number of periodic points grow. Okay, so I want to maybe mention a bit more about the work of Milnor and Thurston and see how this dichotomy comes. But I'll need to, I don't want to, so right, I mean, all depends on this definition of this needing determinant that is a bit involved. And I just want to, I will explain it in the case of unimodal maps, but I don't want to spend the time to explain it in detail in the general case. So, but I do want to mention something. So So there's this mysterious leading determinant. But so what I can say is the following, that, well, first of all, this is the series with integer coefficient that clearly, I mean, from the definition, it's clear that converges on the unities. Okay, so that's clear. Yes. Right, and perhaps the main, yeah, so the definition, let me say that the only depends on the forward orbits of the turning points. Right, it's not that complicated. I mean, say this picture we have 3 turning points, and for each turning point and each monotonicity interval, each of the 4 monotonicity intervals, you cook up some series that encodes the position of the turning point relative to this monotonicity interval. Okay. And you, out of that, you compute some, you put this into a matrix and you compute a certain determinant. That's the needed determinant. Okay. So, but what's important is that it only depends on the forward orbits of the critical points. Okay. And the main result of Thurston is that the Artin-Mazur set of function, the inverse of that is essentially this needing determinant, except that you need to correct this by what they call a cyclotomic polynomial, and this is a relatively straightforward polynomial that you it is easy to define. So it's the product of polynomials of the form one minus f. In particular, they have all their zeros on the boundary of the unities. Okay, so that's basically, this is like the main result of that paper by Milnor and Thurston. So all these properties here really translate into, come from properties of this needing determinant. Now, there is this result from potential theory by Carlson and Polya that tells you that a power series that is exactly this situation. So we have a power series that has integer coefficient and that converges on the unit disk. You have this dichotomy. So it's either a rational function or it has the unit disk as a natural domain. So from that, you can deduce the same property for, so this is really the work of, I mean, that the main theorem of Milnor and Thurston together with this Polya, Carlson Polya. All right. Okay. So there are these two cases, right? So the rational function could be either rational, so the good case in some sense, or it's bad, right? So it cannot be extended beyond the unit disk. So another problem is to characterize those f for which the Artin-Mazur zeta function is rational. So I want to perhaps explain one of the many theorems in Milnor and Thurston, where they characterize, they give a characterization for unimodal maps in the case where the lab number is 2. Suppose. Oh, right. So yesterday we looked at this golden mean, the map, and it's more or less reasonable to expect that if we have a 10 map, pre-periodic turning point. And the Artin-Mazur zeta function is rational. And so the same principle, the orbit separates the interval into finitely many intervals that form a Markov partition. So the image of an interval is a union of intervals of the partition, and you can use that to put some coding, some symbolic dynamics, and reduce the problem to computing the number of periodic points of a subshift of finite test. Okay. So that's basically, and the theorem of Milnor and Thurston is that this is essentially all that an equivalence. Let's suppose F is unimodal, which means that the lab number is 2. Now, in the quadratic family, we need to include the case where maybe the critical point doesn't converge to, sorry, it's not pre-periodic, but maybe it converges to some attracting cycle. So in that situation, we still have this Markov partition, so it's uniformly hyperbolic, and we have a Markov partition, and we can count, the periodic points by looking at a subshift of finite. So the theorem says that the Artin-Mazur zeta function rational if and only if the turning point is asymptotic to periodic example. Okay, so we'd like to, so the plan is that I want to this. Yeah,
Static to periodic cycle is not necessarily pre-periodic.
exactly. Yes, we need to.
Right.
Yes. So for a quadratic map, for example, if the quadratic map is hyperbolic, right? So the critical point converges to an attracting cycle. You still have this Markov partition and this subshift of finite type that describes the dynamics. And so in that situation, the Artin-Mazur set of function is still rational. So we need to include that case. So it's not pre-periodic, it's not periodic on the spot. It's not, doesn't come exactly to itself, but maybe asymptotic to an attracting cycle or any cycle. Okay, so I want to sketch the proof of the, yeah.
Is it enough then to have a repelling cycle in the logarithmic cycle?
Sorry?
Is it enough to have a periodic cycle in the logarithmic cycle, like a repelling cycle in the logarithmic cycle? But you can't have still asymptotic.
Say like for, maybe I don't understand the question. So maybe for, say for the 10 map, it could happen that the turning point is periodic.
Yeah.
And that's, in that case, is some type of expanding, some repelling periodic cycle. And that still gives you a rational Artin-Mazur set of function.
So you can also just approximate a repelling cycle.
Right, yeah.
It still be acceptable.
Yes, like in the case of a 10 map, for example.
I think what he's getting at is that, I mean, another way of phrasing this, if it's a C3 negative Schwarzschild, is either the map is pre-periodic or there is a parabolic or attracting fixed periodic point.
Yes.
And no other possibility.
Right, say for the quadratic family, yeah, exactly, okay. So for the quadratic family, this last part would say that, yeah, so it's either Thurston, so the critical point is strictly pre-periodic, or there is an attracting or a parabolic cycle. That situation, we know that the attracting or parabolic cycle attracts the critical point, and then the Artin-Mazur set of function is going to be rational. Okay. So you could say that it's almost hyperbolic in that situation. And for tense maps, it would be like this post critically finite condition.
Sorry.
Yeah.
That's a very nice question, I would say, but my asymptotic to periodic cycle, you mean the only limit is a cycle or contains a cycle?
So it's a cycle. I think in for interval dynamics, well, no, yeah, it is equal to a cycle. Yeah, it is equal to a cycle.
So here is equal.
Yeah.
Okay.
So the distance, there's a certain cycle where, so you approximate the orbit as a set. Okay, you converges to an orbit. Okay, any other questions? Right, okay, so I would like to sketch the proof, and at the same time, I'll give more information about this mysterious needing determinant in the case of unimodal maps. So for unimodal maps, this is really simple to define, and we will see from the definition how to prove this theorem. Okay. All right, so sketch of proof. So first we define this needing determinant, and this involves this type of needing sequence defined as follows. This is the sequence of plus or minus 1, defined as follows. So going to be plus 1 if I'm going to write it in such a way that it works for both cases. Could be increasing and then decreasing, but it could also be decreasing and then increasing. But basically, in this case, it would be that we are to the right of the critical point. It's going to be -1 if it's on the left. Okay. So we want f to be locally increasing at Fn. Same, but locally decreasing at Fn. And we need to consider the case where the critical point is periodic. And in that situation, epsilon n is defined in such a way that the product from epsilon n up to, epsilon 1 up to epsilon n is equal to 1. So I want to define these as epsilon 1, epsilon 2 up to epsilon n minus 1. Okay. All right. So that's the definition, and then the needed determinant. In this case, it's simply this period. That's the needed determinant. Okay, so from here, I think that's all we need. And from this main result of Milnor and Thurston, the rationality of the Artin-Mazur function is equivalent to the rationality of the needing determinant. Now, what's important to note here is that the coefficients here are of this power series are either plus or minus 1. It's really, really special. And we have such a series that is rational. Now, I want to conclude that the sequence of coefficients is pre-periodic. There are at least 2 ways of doing this, so I'm going to explain one of them. All right, so if we have a power series that is given by a rational function, that means that the coefficients satisfy a linear recurrence relation. Right? Now I said there are at least two ways, so this is one. And we could apply this theorem by Skolem, Mahler, and Leaf. Which says the following: that we have a sequence of complex numbers. Okay, satisfying a linear recurrence relation. Then the set of indices where the sequence can vanish is very special. Okay. It's could be must be composed of some finite set and a finite union of arithmetic progressions. So one of the interesting things about this theorem is that although it's formulated for complex numbers, to the best of my knowledge, the only known proof involves p-adic analysis. So you basically embed this into some QP with a well-chosen P, and you make a certain interpolation. So you show that n actually depends on in an analytic way in the number n seen as a p-adic number. Okay, and using that you can, and this is the only known proof. Okay. Well, anyways, so for us here, when we apply this theorem, well, here we could replace 0 by anything, right? So we could look at the set of indices where we get a -1, and that will say that basically that's this very special set. And since there is one other option, so if it's not -1 is 1, that implies that this sequence is pre-periodic. Yeah, it's a finite union of arithmetic progressions. It's a finite set union, a finite union. So it's composed of a finite set. Oh, finite set. Okay. So we would like to say it's a finite union of arithmetic progressions, except that maybe at the beginning you have some exceptional cases. Okay. Okay, and that's it. That's it. So you use this black box, and then, well, basically, so this is Kolem-Mahler tells you that, in fact, the sequence is pre-periodic. And that in turn implies that the sequence of epsilon is itself pre-periodic. And that implies that we have this condition here. This is saying, so the fact that the epsilon n are periodic, if you look at the definition, tells you that you're in a cycle, the periodic orbit is in a cycle, depending on where you are. I mean, you follow, eventually follow a periodic cycle between left and right, and that forces the critical orbit to converge to a cycle. Okay. Okay, let me just comment. So this is the proof I came up. I'm guessing Milnor and Thurston, that's what they had in mind. And so my student Jorge found an alternative argument using automatic sequences. So basically, if this power series is a rational function, you can reduce mod p. You take some prime number, say at least 3. So now you have a rational function defined over fp. And we know that when you expand it as a power series, the coefficients must be p automatic, whatever that means. So that's a characterization of rational functions over finite fields. But there's another theorem of Kochman that says that if you have a sequence that is at the same time P automatic and Q automatic for a different prime P, then the sequence must be pre-periodic. Okay. So two black boxes is your choice of showing this. Well, it would be nice to have a simpler proof without any black boxes. Yeah.
Which one is the biggest?
Sorry?
Which one is the biggest?
Oh. I don't know. I don't know. I like this one. I mean, okay. Yes.
Like the automatic sequences.
Yeah, that's. I think that is the output of a state machine, P state machine or something. I forgot. Sorry.
Let's make a break.
Yeah. Okay.
7 minutes. That's fine.
Okay. We need to. Okay, so I wanted to mention what happens for multimodal maps. Well, there's the problem to characterize those multimodal maps where the Artin-Mazur zeta function is rational, and there are some interesting examples that I wanted to mention. So it's a theorem by Ruelle, Olivares-Vinales. So basically, what this theorem is saying is that the most you can hope for, so if from the knowledge that the Artin-Mazur zeta function is rational, the most you can hope for is that there's something special about one critical orbit. That's basically the content. Okay, so let's pick some degree, at least 3, and let's look at the moduli space of real polynomials of E having all critical points okay, so in this setting there is a codimension 1 family actually smooth, right, that have the rational Artin-Mazur zeta function. In fact, the Artin-Mazur zeta function is the same for all the elements of the family. We will see an example. So I'll mention the case degree 3 in more detail. So that all but one of the critical points undergoes independent bifurcations. So roughly speaking, we have this family where all of the critical points move independently. They change dynamics except for one of them. Okay, so and all of these having a constant Artin-Mazur zeta function, which is rational. So in some sense, this is saying that the knowledge of the Artin-Mazur zeta function being rational can at most tell you something about a single critical point. Okay. Now, in the case of degree 3, this is quite explicit. Right, so this is okay, that's the idea. So here we have a critical point that maybe I want to place at 0. And then maybe it maps to 1. And it maps to a certain parameter minus t, and then it comes back. Okay, so there's this super attracting cycle of period 3. And there is a second critical point, C of t, which is mapped inside this interval that is invariant. Okay. So I could easily write a formula for this polynomial explicitly, but maybe there's no point in doing so. What's important here is that we have this golden mean dynamics, very much like the golden mean 10 map, where the, let's say, this interval I'm not here, that goes from minus t to 0, mapped exactly to the interval 0, 1, and the interval that we can denote this by 1, and the interval 0, 1 is mapped to the union of I0 and I1. So the interval from minus t to 1. And this interval is therefore invariant. And we can compute the Artin-Mazur zeta function restricted to this interval explicitly in almost exactly the same way as we did for the golden mean 10 map. Except that this is not exactly that. We need this factor. I forgot whether we need to. We have an yeah, this is correct. So okay, so it's not exactly like the golden mean 10 map. What's happening here is that we have the attracting cycle. So we have two periodic cycles of period 3. There's the super attracting cycle, and there's also a periodic point of period 3 at the boundary of the immediate attracting basin. Okay, so compared to the golden mean 10 map, there's an extra cycle of period 3 that accounts for this extra factor of 1 minus s cubed. Okay, but otherwise it's exactly like the golden mean dynamics. And you can check from the formulas that as you vary t, you can go all the way from here. So the critical value could be exactly minus t. And as you vary the parameter, you can go all the way up to even here, maybe Okay, so the dynamics of this critical point is changing, it's bifurcating, because you can, so there's this subshift of finite type here, and the critical value could land anywhere on the subshift of finite type, so the dynamics is changing. And if you somehow zoom out, you can show that there is a cycle of period 2. Everything beyond that escapes to infinity, and everything between this interval and this other interval is absorbed by, it eventually maps to this interval here. So in fact, it's the zeta function of ft restricted to. So this is really describing the so this interval here contains all of the periodic points of the polynomial except for a cycle of period 2, which is outside. So the Artin-Mazur zeta function is in fact constant, equal to the same, where we need to account for an extra cycle of period 2. Okay. So that's the example in degree 3. And for a higher degree, you can do something similar, where basically all of the critical points are mapped inside I1.
Excuse me, can you explain? I didn't understand the beta functions. Fs.
FS is
FT, sorry, yeah.
So you added the factor.
Oh, yes, yes. Okay, so let me draw a zoom out picture of the same story. Okay, so here out. Same picture, but we're zooming out. There's this interval from -t to 1. And maybe this is alpha t. And what I'm claiming is that we have this cycle of period 2. And this is what accounts for this factor, okay, with this extra cycle of period 2. But I'm also claiming that there's nothing else. So if you start with some point outside the larger interval from alpha t to beta t, then the orbit escapes to infinity. So it's not periodic. And if you start anywhere in the open interval between alpha and beta, then this eventually is mapped inside the interval -t1. Okay. So this implies that every periodic point of Ft is contained inside this interval minus T1, except for alpha and beta. Okay. So the zeta function is exactly this zeta function restricted to this invariant interval, except for this extra factor that comes from alpha and beta.
So you mentioned that the function is going to be constant along this submanifold that you have in the parameter family.
Yeah.
But then I'm guessing by transversality, then one of the other critical points undergoes a bifurcation and generates another like one-dimensional family. The function will be the same either along that link, right?
Right. Yeah. So here, for example, we have a dimension 1, which is codimension 1 in the moduli space of cubic polynomials. So it's a dimension 1 family where the Artin-Mazur zeta function remains constant, and we see that the this critical point is having bifurcations, right? So the dynamics is changing, right? If we put some coding here, we we can use the Fibonacci subshift to code the points that remain never are not attracted to the cycle of the orbit of zero. Then this critical value, the critical value of this critical point, could be any of those points in A1.
So it could induce itself a local version of the function that will have to agree with the, because you can also undergo like a similar like critical. Yeah, you could become periodic. It could have like a free cycle. You could play the same game.
Right. Yeah, it could be periodic. It could have infinite orbits.
Yeah.
Yeah.
Yeah. So then, like, you can have two foliation intersecting transversally, which the zeta function will be constant among both foliations. It's going to be the same, right?
Well, I'm not so sure. I mean, if you well, I mean, okay, so you could consider an extra parameter that somehow changes the, so that the zero is no longer periodic, but it's still going to be attracting. Okay, and you have more or less the same structure. Okay, so though you can embed this in a two-dimensional family, only one of the critical points is bifurcating.
Yeah, but you can play the thing is that you can play the game with either critical point, but there's no preference in one or the other. And so these two four-dimensional ones have in mind the sector earthly.
I'm not sure because, well, at least in this example, one of them is periodic. So I wouldn't know how to, I mean, if they intersected, you would have, in the intersection point, you would have both critical points periodic, and maybe that's stable. Yeah, so.
But you can play the game in high dimension, more critical points, you could play similar game with this.
Right, so let me discuss the higher degree. So basically, so the idea is quite similar. There, you could have situation where maybe all critical points are mapped inside a knot. And so provided these say zero has the same dynamics, it's always a periodic point of period 3, you still have this structure where you can just you have this invariant interval, and the periodic points inside are described by this Fibonacci subshift. Okay, and all the remaining critical points are mapped inside this invariant interval, and they move somehow independently, right? So you can use all of these. You need to maybe use Thurston's theorem to show that there is such a polynomial of degree D, and maybe some transversality result to show that the critical points move independently. So you can keep this periodic cycle of period 3 while perturbing all the remaining critical values independently. Okay, but it's essentially the same principle. Okay, same idea. All right. Any other questions?
If you have, so here you've got one restrictive interval and you've got dynamics there. If you have two, let's say, separate restrictive intervals, and you've got dynamics here and dynamics here, and you have a zeta function for this map and a zeta function for this map. If you combine the two, it's just the sum of the two zeta functions, isn't it?
It's the product, but you may have, you also need to account things that maybe never enter those two.
Sure, but yeah, those we can.
Right. So the point also here is that you can show that outside of this restrictive interval, there's essentially only one orbit that you understand. Okay. Okay, so this was supposed to be for the first day. Right. Okay, so maybe I'll change gears and yeah. And yeah, so I would like to discuss now the case where we count points with weights. Okay, so we, instead of counting just the number of periodic points, we want to introduce a function that will give a weight to points, and we want to count periodic points according to that weight. Okay. Now, so one of the highlights is that in doing so, you have these prime orbit theorems that resemble a lot the prime number theorem from number theory. Okay, so I think I can go over the setup. So okay, so we have, as before, political space and continuous map. And we fix function that maybe continuous, maybe not. And this is called this is going to be the weight or potential. I'm going to introduce some notation. So I want to denote in this way the set of fixed points of Fn. And we will also need the Rivera sums. Hey, and I want to introduce somehow a new parameter, E. And this partition type, I mean, you're familiar with statistical mechanics, this would be the analog of the partition function. So we sum over the periodic points period n t times f and phi. All right. So perhaps a more okay, let me. Yeah, so maybe more symmetrically, in a more symmetric way, we could do the following. So this is so what I want to say is that this is really we're summing along the orbit, the periodic orbit. So you could write this in a more symmetric way. And maybe I'll do this in a minute. Okay, so the dynamical zeta function weighted or Ruelle function is defined as follows. The same as before. So instead of writing the number of periodic points, we count them with this weight. And we need to multiply by this. Great. So if we take the potential or the weight to be constant equal to 0, here we're just counting the number of periodic points here, the number of fixed points. So I didn't write isolated fixed points, maybe I should. So in the case the weight is 0, this is just the number of isolated fixed points of Fn, and the zeta function is just the Artin-Mazur. Now, in this generality, we can also write down this Euler type product. Where can write the Ruelle zeta function as a product over now periodic orbit. I forgot to introduce some notation. Okay, so here we want to consider the set of all periodic points. And this Euler product is best expressed in terms of periodic orbits as opposed to periodic points. So far, we have been always looking at periodic points, and we are counting periodic points. Now, the Euler product involves periodic orbits. So there's a subtle difference there. So let me tell you some notation. So we define, well, first the minimal period. And P hat is going to be the orbit. And also use the period of the orbit. And set up periodic orbits as opposed to periodic points. Yeah, I think that's what I need. All right, so here we have a factor.
Phi must be L1 or
Yeah, so that's an important, somehow crucial. So the nature of phi is crucial. Okay, I'll soon, maybe unfortunately tomorrow, restrict to the case where F is a rational map and phi will be the geometric potential, so minus log the norm of F. However, you could also, I mean, another important setting is where you take phi to be Holder continuous. Okay.
Or combination.
Sorry?
Maybe combination.
Or maybe combinations of both, yes. Right. Yeah, but up to here is everything formal. We're not worried about convergence, it's just pure, it's a formal identity for now. Okay, but that will, I mean, what you're pointing out is somehow central in what comes next. All right, so here we can write this zeta function that is defined in as a series as a product, and we have these. So we have S raised to the power to the period, minimal period. This is very similar to the Artin-Mazur zeta function, where we had up to here. This would be the formula for the Euler product of the Artin-Mazur zeta function. But we have an extra factor coming from the weight. And this is where we can write things a bit more symmetrically. But if you prefer, this is just S of I hat phi as for any point P prime in the orbit. Okay. And as we will see, there are certain analogies with the Riemann zeta function, okay, where similarly you define the Riemann zeta function as a series with summing terms. And what makes the Riemann zeta function so special is that you have this Euler product. I mean, one of the things that makes the Riemann zeta function so special is that you have this Euler type product where you have now these the prime numbers appearing explicitly in the formula. So we are connecting on one side the analytic part to the, for the Riemann zeta function, you would have the number theoretic part. In this scenario, we have some analytic formula for the Ruelle zeta function. And on the right-hand side, we have information about the periodic orbits. Okay. And this is more or less where the prime orbit comes from. By similar reasonings, you can deduce some asymptotics for the counting of periodic orbits with weights by analyzing the zeros of the Ruelle zeta function. Okay. Now, what's perhaps lacking here, so the Riemann zeta function is also special because you have this functional equation, symmetric, essentially symmetric. Here, I don't think we have anything analogous to that. Right. Okay, so let me maybe say a word about the convergence of this function. So what can we expect about the convergence? So we can maybe focus on the series here. And it's basically the root test, right? So we want to know what's the exponential rate of convergence of this partition function, Cn. So this leads us naturally to, oh yeah, I forgot to say something. Sorry, I forgot to say something. So, right, so I mentioned that if we set the potential to be 0, we have the Artin-Mazur zeta function. Now, I'm going to do something terrible, which is that I want to forget about S. Okay? In fact, S is a bit redundant here, because if we consider, we could incorporate, another way to say it is that we could incorporate S inside the potential in this way. So we could find a new potential psi in this way, and the zeta function for this potential with S equal to 1 would correspond to the same, but without the term S to the n. So we may choose to somehow get rid of S of n by incorporating it inside the potential. So this is really about this Ruelle zeta function is really about the family of potentials. And there's some freedom in the choice, depending on the problem, you may want to consider one family of potentials over another. And for the prime orbit theorem story, the family of potentials we want to consider is this one. So S equal to 1. Okay, so right. So from now on, I want to set fix S equal to 1 and now that this is terrible because this same notation for that be using for the Artin-Mazur zeta function. But from now on, this notation is for the dynamical zeta function where T is the parameter that goes with the potential. Okay, so sorry for the, so there's an abuse of notation here that, well, okay. All right, so for convergence, and maybe I'll finish with this. This is basically the root test. So we want to analyze the exponential rate of growth of these partition functions, and this leads us naturally to the pressure function. So we want to look at these numbers in the link soup. as n goes to infinity of 1 over n log n of, so this is the pressure function of pi, maybe later a drop dead pi. And the upshot here is that so if we know that for a certain parameter T naught, the pressure function is negative, then we immediately have that the dynamical zeta function converges on the right half plane starting from T naught. So locally uniformly.
So your definitions before were for complex T. I don't know.
Yes, that's a good question. So yes, it's complex.
Okay.
Complex, yeah. We allow complex.
Just to know.
Yeah. So everything is formal. So yeah. Now, T naught is real though. So if we know that for a certain T naught, the pressure is negative, then we have convergence on that right half plane. So, so we will see. I mean, in good cases, at least, we have this Bowen formula. Where the pressure function vanishes precisely at, well, depending on the context, maybe 5, the geometric potential, the vanishing point will be the Hausdorff dimension of maybe the non-wandering set or the Juliet set. So we, at least from basic analysis, you can see that we should expect convergence up to whatever the Hausdorff dimension or the first zero of the pressure function. And maybe in good cases, there will be a simple pole at that number. Okay, so it's not unlike the Riemann-Zeta function where we can easily see from the series that defines it that we have convergence on the right plane of real part bigger than 1, and there is a simple pole at 1. So that's, so you can start to see that there are certain analogies with the Riemann-Zeta function. Right, so the plan for tomorrow is we'll maybe start with a complex rational map and take the weight phi or the potential to be the geometric potential. And the aim will be to discuss these prime orbit theorems.
Before you go to announcements, first the short one. If you are staying outside of Inban and you need some place to work here, please go to Felix. Felix has some spare rooms he might be able to find for you. And the second announcement is today at 7 o'clock in the evening, there's a conference workshop dinner at 4th floor. You're 4th floor, you'll invite, please come. It's not a Wi-Fi or something, so just however you want. And I think I said everything.
Something. We will think about making a photo now at the common. If you have adequate good mobile phone or camera, but I don't have. I will ask, but I wanted to ask you to gather the.